So let's explore recursion. And while we're going to be exploring recursion in the computer science and programming context, recursion is a concept that you see show up in many other places and disciplines as well, such as in art. And M.C. Escher is famous for works of art, such as this one, where it's a photo that, or an illustration that feels a little bit confusing. It's hard to know where something ends or begins when something is defined in terms of itself. But we're going to unravel this mystery in the context of computing in this lecture. A recursive function is one that calls itself, is one that where inside of the function's body, there is a function call that the function is able to refer to itself internally. So it's as if the function is aware that it exists and it knows that it can make use of itself. You can think of this as a function that is defined in terms of itself. And that's often how you think of it in a mathematical context. This is a really beautiful and powerful concept that allows us to express many complex algorithms very succinctly and beautifully, right? And we'll get a feel for this as we move forward in today's lesson. One of the things you should know is that anything you can do with a loop, you can do with recursion. And the same is actually true and vice versa. These two are two shades of the same type of computation that we can work through underneath the hood, but they take very different angles of approach. And some problems are much simpler when expressed recursively and feel more natural to do so. So we're going to be taking a look at some of those types of algorithms as well. To give you a sense of how this works in code, and just to convince ourselves that this works at all, like we just move through an environment diagram, but I want you to actually try running some code that involves a recursive call before we continue on. So if you'll pull today's lecture materials, that's lecture 16, npm run pull, and then npm start your server, there's a application that we're working on, the OO Recursion Demo app, and we can see what we've got that we're working with here. So if I open my code up on the left, I have the OO Recursion Demo app. You'll notice that in the main, we're just printing a few diagnostic messages about when this function call begins and when we finish it. And then in between those print messages, we're calling f of 0. And we see an implementation of f that is pretty close to what we traced through in the environment diagram, but slightly different, right? There is no recursion currently in this implementation of the function f, but that's what I'd like you to try and do on your own in this hands-on. So go ahead and try pausing the video here. Try following these instructions on the slide. See if you can get the recursive call to be correctly evaluated, and then resume the video once you've done so. All right, so I'm going to switch back to my VS Code and my browser. And the first thing that we're trying to do is actually add the recursive call. So notice that when, as we traced through before, in this else statement, the instruction said under this print call where we print recur, try calling f again and give an argument value of n minus 1. Right? And the -1 here is important, we'll come to learn, because that's changing the value of n, our parameter, in a subsequent call. Kind of like in a loop where we need to increase or decrease some counter variable closer to our exit condition. This is bringing us closer to what we're going to learn is called the base case, which is where our recursion stops. So notice in this branch of the if then else, we don't have a recursive call to the function f. Okay, so I save that, and we hit our base case immediately, right? So we need to change our call in main to say 2, where 2 is going to be the first value of n. And so now notice the difference in our output, right? So we call f with 2, we enter f of 2, and then we hit this recursive case where we enter the frame of f where n is going to be 1. We recur, we enter f of 0, and that's when we hit our base case. This is the exact same code that we traced through before effectively. And then notice as we return back to each subsequent frame in our function call sequence, we're going back up our call stack as we saw in the environment diagram, and we're exiting each function one by one, such that when we print n each time, it looks like we start from our base case where n was 0, and then we go back to the function frame call where n was 1, and then n was 2, and then we get back into main, all right? Now, if you wanted, you could, the computer is very happy to evaluate much larger values of n here. So if n of 20 would give us the same pattern, but with a larger range. So 20, 19, 18, all the way down to our base case. And when we get to the base case, notice we pop our way back up the stack until we reach the main function frame and our program evaluation is done. Right? So this is an example of a recursive function, and we've convinced ourselves that the computer is more than happy to evaluate a function that has a call to itself from within its definition. So let's talk a little bit more about the mechanics of what we're seeing here and some of the things we need to be careful with when we are thinking about writing recursive functions. As I mentioned, recursion relies on each function call having its own frame on the call stack, right? If you imagined a world where a function only had one frame for any time you called it, this wouldn't work, right? But because the way our environment diagrams are set up and the systems that implement this under the hood of our programming language set up new function call frames anytime a function call is encountered, and each of those function call frames keeps their variables separate from one another, this is how this phenomenon is able to work. And it's actually quite beautiful that it applies the same principles we used in another context, but extends upon that in such that we can call a function in terms of itself. And it all works out in a very predictable and reliable way, thanks to our call stack having our variables separate from one another. The other key thing that the environment diagram provides to us that our system needs to keep track of under the hood is when a function call returns, where do you go back to? Where's the bookmark that you left somewhere else in your program? And we write this in as the line number of our program, right? And so when we made the function call in the outer part of our code to f of 20, remember the return address here would have been line 5. So in the very first call to f in that frame, its return address is different from the recursive calls, right? So in the recursive calls, when f was 20, the next call to f would have occurred on line 15. And this would have been true for all of the other frames until we reached our base case. And so those function calls to f returned back to line 15 until finally, when the frame where n was 20 reaches the end, it goes back to main, right? And so another key piece of how recursion is able to work is this idea that we're leaving sort of a cookie crumb trail that we can trace our steps back to get back to where we came from and properly evaluate a program. This is another reason why we've really emphasized trying to add those details to the call stack in our environment diagrams. And what I hope you'll believe me is that trying to evaluate recursion without having a sense of what's going on in, say, an environment diagram would be very, very confusing and perplexing. As I mentioned before in the previous video, you've been doing this all semester. The same dynamic takes place. We just have to be a little bit more careful to make sure we're working in the right frame and we're going back to where we should with our return values. So I want you to pause the video for one more moment and try and imagine what happens when this code runs. You don't need to draw this out in an environment diagram, but just try and think through it at a conceptual level and see if you can identify something that might be concerning about this particular code listing. All right, well, let's actually go try and open up a file that implements this exact same piece of code. So if you'll open up the O1 Stack Overflow app example. So I'm going to switch my code here. This is the exact same piece of code that we had. And try running it, and let's see what happens. All right, so here we go. I'm going to navigate in my browser back to my example for a Stack Overflow, and we see, okay, it looks like this thing's running. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, negative, uh-oh. And then we look at our scroll bar over here, and wow, that's pretty small. Uh-oh. Seems like something's going wrong here. So if we go all the way to the end, you'll notice we get an error message. And the error message is maximum call stack size exceeded. Now, this is something you, at this point in the semester, can actually maybe reason about what might be happening here. So notice we're all the way down to the frame where f has an n parameter value of negative 11,418. Yours might more or less vary. But at some point, we reach this error that says, hey, our maximum call stack size exceeded. And I want you to imagine drawing an environment diagram where you had 11,400 frames on it. And at some point you're gonna give up, probably well before you have 11,000 frames, right? But the computer is doing its best. At some point it realizes, hey, we're using more memory as we add these frames to the stack. And it looks like this isn't going anywhere. It reaches some threshold on the call stack. These are the frames that you're adding for each function call, such that it eventually gives up because it doesn't look like this is going to terminate. And before we run out of memory, we'd rather just crash your program and reclaim any memory you used for your call stack so that we leave your computer in a good place, right? So this is actually quite nice as opposed to an infinite loop that'll keep running. Like the computer doesn't know whether or not to stop running your loop, and your loop isn't taking up any more memory. But here, if we have infinite recursion, it leads to this this error occurrence of a maximum call stack exceeded, and our program crashes pretty quickly, right? So there's this meme that I love, and I'll just let you appreciate it on your own for a second here. And this is what we just experienced, right? We're learning how to program. This was a recursive function, but it didn't have what we call an exit condition, or what we're going to call much more commonly in this course, a base case, right? And so if you don't have a base case, you have what we call infinite recursion that leads to a Stack Overflow error. And so as I mentioned, every time a function gets called, your computer has its own internal call stack in memory that has its frames, just like we've been drawing out, and it's adding new ones as this program gets evaluated. And eventually it just runs out of space and says, hey, I don't think this is going anywhere productive, so we're going to crash your program with what's called a Stack Overflow error. If in the course of this semester you've encountered the website stackoverflow.com, which has answers to commonly asked programming questions, this is where that website gets its name from. So how do we actually prevent stack overflows, and how do we write, more directly, how do we write recursive code that won't infinitely recur? The same way, it turns out, that we prevent infinite loops, right? Or effectively the same way we think about avoiding infinite loops is how we need to think about preventing infinite recursion. The same concept transfers. We need some kind of a condition, some kind of a point at which we split. We have a fork in the road. We say, okay, in one case, we're going to recur and we're going to call this function itself again. In the other case, we're going to stop. We're not going to do that. We're going to start returning and moving closer and closer back to where we came from and start popping our frames off of the stack, right? So the point at which we reach a test condition that doesn't lead to further recursive function calls, that is what we're going to call the base case. Not only does your function need to have a base case to avoid infinite recursion, but we also need to change something about subsequent recursive function calls to bring us closer and closer to the base case. Typically, what we're going to see this semester is that's going to be an argument that's changing. So in this in the first example and in the environment diagram we started with, you saw an argument's value changing. We were counting an argument down to 1, 0, and then 0 is our base case, and then that's when we reached it and we started returning back up our call stack. So what I'd like you to try doing with me here is we're going to add a base case to this example. All right, so let's go ahead and do this. And let me have my example open here. So if we want a base case, we need some kind of a test condition. So I'm going to add an if statement. And if n is, say, less than 0, we will simply print base case. Right? Else. And what I'm going to do is I'm going to put that recursive call inside of the else branch and print recursive case. Right? And so this is actually going to bring us to a code listing that is very similar to what we saw previously in the earlier example. And I'll give you a second to type that as well. And what I want to point out is this is our base case, right? So this is the condition in which when n becomes less than 0, that is when we're going to reach the base case. So this is actually a slightly different base case than we saw in a previous example where n was less than or equal to 0. This time around, notice -1 was going to be when we actually hit that base case, not 0 itself, right? So if we wanted to bring it to be exactly aligned with the previous example, I could change that to less than or equal to 0, save my code, and notice that when we enter the frame of f where f is 0, that's when we reach the base case and we start returning our way back up our call stack. Okay? So this is our base case, and notice that in the recursive call here, we are changing something about subsequent calls, right? So in this first call, we're calling the number f with a value of 10. And then in subsequent calls, each time around, we're saying, okay, take our current value of n and subtract 1 from it. And notice that that's bringing us closer and closer to this base case. If I had accidentally forgotten to change n in such a way that it would bring us closer and closer to this base case, notice that we would still have infinite recursion, even though this function does have a base case defined. So entering f of 10, entering f of 10, f of 10, so on and so forth, right? So we need to be making progress closer and closer to our base case each time we make a recursive call. That's one of the important rules of avoiding infinite recursion. After you have a base case, be sure each recursive call brings you closer to it. And just to make an even sillier example here, let's imagine we accidentally went in the wrong direction. So if I added 1 to n at this point, notice the problem is just the same. We're going to have infinite recursion here because f is 10, 11, 12, 13, and we're counting up. But our base case was when n was less than or equal to 0. So we needed to be moving closer to it by subtracting from it, right? So we can see that we eventually get to 11,000 in the positive direction, and then we hit our error there. So the key thing to remember as we're thinking about recursive functions and how to avoid infinite recursion, we need to be sure that our function has a base case defined. And in Comp 110, you're always going to see us define the base case first. That helps us avoid forgetting to have one. And then in the recursive case, we need to be sure we're making the call such that our arguments are bringing us, the way we're changing our arguments in subsequent calls is bringing us closer and closer to our base case. What I just described in talking through the code that we saw in VS Code is also in the slides for reference purposes. If you're just looking over this later in studying and want some reference without having to watch this video in its entirety. So every recursive function needs a base case, just like every loop needs some terminating condition to be sure that we don't infinitely recur. So that's our introduction to recursive functions. And what we're going to do is we're actually going to practice learning recursive functions in terms of working through what we're going to learn is called a recursive data structure in terms of a linked list. And this will give us a more interesting application of why would we want to use recursive functions and how would we apply them to real-world problems.